All right, recording resumed. All right, so I was going through this presentation. I hit with you guys thermodynamics and heat transfer topics. We covered materials, engineering topics, and we're like right at the end. We just got these couple slides. So right as you guys were walking out the door, I was talking to you guys about steel reinforced concrete. Right, so a little bit of history of concrete. The ancient Romans, 2,000 some years ago, did have their own version of concrete. Yeah, all right. It was a little bit different formula than we use today. Here's like modern day concrete. Modern day concrete is this combination of materials. Right, we've got this coarse aggregate, fine aggregate. Actually, you want a different. You want what's called well graded concrete. So you want different size aggregate. It creates the strongest concrete for okay. You pour in this Portland cement and water, and the water doesn't evaporate. No, it's actually a chemical reaction. It's called curing. Actually, I think I remember reading even like the Hoover Dam back like almost 100 years ago is like still curing to this day. Right, it's an exothermic process, gets warm, the whole deal. Right? Now the Romans had their own version of concrete, and then when the Roman Empire collapsed, that technology was lost to history for like a couple thousand years. Right, this was sort of rediscovered, I think, in like 1800s. Right. But there was one thing that the Romans could not do with concrete. They could build lots of cool things, right? They could build aqueducts and roads and walls, right? But what they could not build is what you guys are sitting on right now, which is a second floor. Right? They tried building the second floor, but the second floor is always just crumbled. So say, okay, because concrete is really good at compression, but it's terrible at handling tension. But then this was actually it was invented. I read that haphazardly. There was like some guys trying to invent or make things like plant pots, right? Anyway, right. So he mixed together like steel and concrete. Now, steel or metals in general are really good at handling tension. So here's the tensile strength of steel. Here's the compressive strength of concrete. Now you have a composite material that can handle both. That's what you guys are sitting on right now, right? So the floor wants to bend as we're like putting our weight on top. It wants to bend like this. But the fact that the steel is able to handle the tension, right? You guys see how that works? Now, as a complete quirk of the universe, these two different materials, this concrete and this steel, have the same or very close coefficient of thermal expansion. So as it warms up during the day or cools down at night or summer to winter, these materials will actually expand and contract together, which means it won't all break apart. So just luck of the universe, that happens to be the case. Okay. And I've got one more on materials. And this is just personal interest, I guess, something called catenary. So if you hang a chain or a string right, from both ends, it will naturally create what appears at a glance to be a parabola shape, but it's not a parabola. It's for a long time, way back in history, hundreds of years ago, was for a while thought to be a parabola, but it's not. It's called a catenary. It's some complicated formula you could do. Right, but that will be how the train naturally hangs. Now, if you solidify that and dunk it upside down, you create what's called a catenary arch. And this is the strongest type arch shape that you can create. So if you have some kind of compressive force from above, right, like if you had any other shape, it would just be like weaker. Right now, of course, you can make it like narrower or wider. So that's another aspect to this too. Right? But you see these constructions sometimes, right? St. Louis Arch. You guys know St. Louis Arch? Right? It's actually a modified version of catenary. No, it's not like the pure platonic shape because it's thinner near the top and it's thicker near the sides. But if you take that into account, then it is its own version of a catenary also. It's just like a modified. Right. All right, now we're going on to harmonic motion. Now, you guys actually did cover harmonic motion because AP actually left that in for AP1. So we'll review this real fast. You guys remember time period for pendulum? Now that's like back and forth, follows this expression. You guys were just tested on this a week ago. So I'm sure you guys know that. I threw this one, you guys, this was actually in your college physics textbook. AP doesn't ask about this. But what if you have something that's not a classic pendulum? Like what if the mass is not all like in the bob? Right. But I do want you guys to see that this does simplify to this. Right here. You guys remember I for a point mass could be mr squared, right? In this case, the r would be L, so r and L are the same thing. And if I put ml squared up here, you guys see one of the L's cancels and the m cancels, and oh, that leads you exactly back to this, right? So this is just a general version of this more specific version. Okay, right, guys. Right, so cool to know. I'll say block on spring. This could be vertical or horizontal. This applies to either one, as long as there's no frictional loss. And what we're really leaving out here too is something called dampening. So it's possible that you guys take physics in college and they also saying, hey, given enough time, this will eventually like slow to a stop, right? And different springs might have different like a dampening to them. So we're not even going to touch that. Okay? Now, looking at this oscillatory motion, suppose I have one vertical bouncing up and down, one horizontal, no friction. That sliding is also bounce back and forth, right? their motion could be described by sine and cosine curves, which you guys might remember from unit circle, could describe how far right or left you are. That's like cosine, or how far up or down you are in the unit circle. That's like a sine, right? So what if you were watching a car go like in a circular motion, like from a helicopter? We're in a helicopter point of view, aerial point of view, right? Watching this car go around, right? And so those would always, that car would always line up with the X and Y coordinates of these two masses on these springs, like bobbing either back and forth or up and down. Okay. We did all this, just really review for what you guys were just tested on, right? Right. Frequency and time period are reciprocals of each other. Actually, this just show up on your FRQs, didn't it? Right. This was this was part of the explanation for one of those FRQs yesterday. Right now, I want to hit this one down bottom left corner. That omega, that curly looking W, it's Greek letter omega. We usually use in this class for angular velocity, like how fast is something rotating? Like the Earth rotates one revolution every 24 hours is a version of that. But in this context, it's not that. It's called angular frequency, which is a type of frequency. You just take the regular frequency, 1 over the time period, multiply by 2 pi. Now, why would you do that? Because it helps make these graphs right here, right? I think when I showed you guys these graphs, I did sine, cosine, negative sine. I went back and changed it more aligned with how AP does it, which I think is actually better. Look, let me do a timeout here. Let's zoom. Okay, we're good. Resume. Right. So the reason I like starting with the cosine better is because you start with a displacement. Like if you pull something back, it starts from a displacement. So if you let it go, then it can start to naturally oscillate. Right. Okay. So, but especially if you're in calculus, I think at least half you guys are in calculus. Right. You see a calculus relationship, right? The rate change of cosine is negative sine. Rate change of negative sine is negative cosine. This could be a 4-part pattern, right? And you could just like keep going back and forth. So you could just sort of continue this forever. Right. And go back to this angular frequency. You guys remember something called the chain rule? Well, if you're in calculus, you guys remember the chain rule, right? So that angular frequency, this 2 pi f, you can very easily pop out. Oh, there's the chain rule. Pop it out again. Omega squared. Right? You guys see that? And the amplitude is okay. That just is a constant that you can multiply down. Okay, you guys see that? Great. So yeah, really helps to make sense of that if you've taken calculus. But right, there you go. All right. All right. Oscillation linearized. Okay. This I had to make because AP loves that when you linearize graphs. Right, you guys had to do that on your FRQs also for distance of time, right, for an accelerating system. But they could have asked you this. They very well could have asked you this, right? So there's a couple ways to do it, not the only ways, but there's some ways to linearize that data, right? Okay. All right, so that's all the oscillation stuff that, yeah, actually you guys were tested on last week. Right, so now moving on to stuff that I may mention this to you guys. I don't remember. I don't know. If I did, it was really brief anyway. But let's do wave properties. Now, if you go back a few years ago, AP used to ask about waves, but they dropped it. They dropped that topic, I think, when the pandemic hit. Right, so you're looking at what's called a classic transverse wave, and has some properties. Right, so okay, so frequency and time period are reciprocals. You guys know that already, right? There's a little bit of crossover between this and oscillatory motion, right? Because I mean, there's got to be, right? But you guys see this bottom right formula right here? This is speed. This v is velocity, like speed, right? Right, and it is equal to wavelength times frequency. Okay, so wait, now what is wavelength? It's the smallest part of a wave that can self-repeat. So you could measure it crest to crest. See how I measure crest to crest here? Or you could go from this node, one full S curve shape, to this node. See, it's like one S shape. I guess that. Right? But just if you identify any smallest part that will self-repeat. Okay, right? And then frequency, of course, is one of the time period. Maybe this wave is in motion. Maybe it's propagating energy left to right, for example, or maybe it looks like a standing wave. Right? However you do it, there's still a frequency associated with that. Okay. Let me go back one more time. Right, so just make sure you guys know. Suppose they do like 2 beats per second. Right, I don't know if that's exact, but it's pretty close to 2 beats per second, right? What do you guys say the frequency is? 2 hertz, 2 hertz, right? And what's the time period between beats?
0.5 seconds.
0.5 seconds, half a second, right? Okay. Oh, okay, so you guys get all that. Right, now there's actually 2 main categories of wave propagation. The easy one to draw is the transverse wave. You just like whip off like that could be a sine curve right there, right? Right, sine curve, sine cosine. The one that's harder to draw is the longitudinal wave, also called a pressure wave. Actually, how you guys are hearing me right now? Are you hearing my voice because there are sound waves propagating through the air? Right? Does sound need a medium to travel through? Can sound travel through a vacuum? No, sound cannot travel through a vacuum. You ever heard if you scream in space, no one can hear you? Right? Sound needs a vacuum. Or sorry, just scratch that. Oops, opposite. Sound needs a medium. Sound needs a medium. Right, and between my voice and your ears right now, is something like this. The air molecules are like bunching up further apart, bunching up further apart. Okay? is having a certain frequency, right? If it's a higher frequency or a lower frequency, right, then these might be like spread out, like different wavelengths, but it's all the same speed. It's all the same speed, approximately 340 meters per second, depends on the temperature, right, and the pressure. Okay, but these are your two main types of waves. Introduce some other ideas here. Interference. So constructive and destructive interference. I actually have some cool videos for these, but I'm trying to give you guys the fast version. Suppose you have two wave pulses headed towards each other. If they cross crest to crest, they'll make, say, 2 units plus 1 unit make 3 units. And then they will actually just continue after straight through each other. So I could have a diagram after this, and it just show them crossing straight through each other. You can find videos of this too, right? Destructive interference. Well, what if you have plus 2 units here and negative 1 unit here? When they cross over, 2 plus negative 1 is only positive 1. But then, like, weirdly enough, these pulses will actually just go ahead and cross through each other. You can do this with a rope. You can do like positive pulse and negative pulse, and they will actually cross straight through each other. So actually, the one I have labeled after is really just like the snapshot where they happen to be lined up. Okay, right. Constructive, destructive interference. Okay. Oh, actually, continuing on at destructive interference. I know I'm showing transverse type waves here, but this also works for longitudinal waves. How many of you guys have ever worn noise canceling headphones? Noise canceling headphones. Okay, the way those work is they take the ambient sound of the world, right? They invert it, right? Switch all the high and low pressure points, mix it with that ambient sound, and it effectively creates destructive interference that creates like no sound that goes into your ears. It's an active process. It's not just a bunch of insulation. It's an active process of destructive interference. Okay. All right, let's look at interference pattern. So suppose you have a couple, you guys see there's like a wall down here with a couple of slits in it. There's this very famous Young's double slit experiment done like 100, 200, I think almost 200 years ago. Okay. Where anyway, if you want to determine does something exhibit wave-like properties, one way to define a wave is that it will do this, right? It will propagate waves out here. It's called Huygens principle. And suppose you have a back wall here. You guys see how there's constructive, destructive, constructive, destructive, constructive, destructive interference. We're looking at like a wave press. That's what these green lines could represent, right? Maybe like ripple waves, right? Right, and you'll get an interference pattern on the back wall. Now, if you shine light through these two slits, you'll traditionally also get an interference pattern, which is evidence that light is wave. It was a question for hundreds of years: is light fundamentally a wave, fundamentally a particle? And for a long time, it was thought this experiment established light is in the wave box. Right now, there's an update to that story at the end of this presentation when we get to quantum mechanics. It's actually it ends up being both, but we'll come back to it later. All right, resonance and closed pipes. Okay, now we're back to longitudinal waves. You guys see these dots could represent air molecules. Now this is a lab I do, used to do with AP, do with my other classes. Did I possibly demo this with you guys? Did I demo this with you guys? Maybe, I don't know. Here, I'll tell you how this works. You take a PVC pipe, you dunk it in water. Now the purpose of dunking it in water is that the water effectively closes one end, but you can raise and lower that pipe to effectively change the length of the pipe. You guys see how it's going to be open on the top, but the water line closes it on the bottom, okay? And then you can take a tuning fork and strike a tuning fork, bing! Now, every tuning fork, there's some associated frequency. Like an A note is defined as 440 hertz. Well, according to some definitions, depends on, right? Okay, so if you raise and lower that pipe, at certain places, it will resonate, right? Actually, the two places I've drawn here, it will. So you raise and lower that pipe, it's not like this. Notice it's not changing pitch, but it's changing amplitude, right? And it'll resonate. So if you got a high pressure point here and a low pressure point here. Now, if you approximately triple that, not exactly for some reasons, but kind of gloss over that, but approximately triple that distance, you'll get another place where it's and it'll resonate again. You can use that to figure out the wavelength of the wave. If you know the frequency stamped on the tuning fork, you can do speed equals wavelength times frequency, and you can calculate the speed of sound. I like to do this lab. Some of you guys might be physics teachers one day. It's a really good lab to do. You should get about 300 something meters per second, right? All right, so here's places that'll resonate for a pipe that's closed at one end. I say closed pipes, but really closed at one end. Now, if you close the other end would say you were inside like a chamber, like a closed chamber or closed room, then both ends should be high pressure points. But if it's closed at one and open at the other, like this one, then high pressure point at the closed and like a low pressure point closer to a vacuum on the open end. Okay. All right. What if it's open at both ends? Right. This was an NFRQ question years back when they used to ask this. Right. What if you have like wind blowing through a pipe? Right. Or what if you have some version of that? then you'll have high pressure points on both ends. Now, these are places where it would resonate, right? Think like musical instruments for either this or this, depending on how you think about it. These could be maybe like flutes or recorders, like wind instruments, right? Brass instruments, organs. They kind of all work on this principle of like pipes, air flowing through pipes. Right? Notice too, I whipped off transverse waves. You guys see that? Let me go back to the previous slide. It's really hard to draw longitudinal waves because you have to sit there and like draw a bunch of dots, and then you have to make them bunched up correctly so that the person interpreting the diagram understands that these are high pressure points here and here, right? That's really hard to do. So it's really common to represent longitudinal waves with transverse waves, even though they're not really transverse waves, because it's really easy to just whip off an F shape, right? You guys see that? Okay, right. So same thing here. These aren't really transverse waves; they're just represented that way. Okay, they're actually longitudinal, right? Right. Okay. Now we're back to actual transverse waves. Let's look at like waves on a string. I think like, ooh, if you pluck a guitar string, that could be like this one right here, right? Okay. Now, remember I told you guys that one full wavelength could be crest to crest or one full S shape. Do you guys see how this is actually half of that, right? It goes from this node to this node, but that's like half of an S, and then you need like another half to complete the S, right? So this is half of a wavelength. I could say L equals 1/2 of lambda. The length of the string is only half of the full wavelength. Or you could dunk that backwards and say the wavelength is twice the length of the string. You need twice that string to complete the wavelength. The one right below it, the wavelength and the length of the string are the same. 2/2 is just 1. So one full wavelength is the length of the string. You guys see that? Okay. All right. And then, okay, you can keep going, but you guys see that there's this pattern set up with like standing waves. Now, one thing that, one cool lab you can set up, well, versions of labs you can set up if you have the right equipment. Again, I've got videos for this. If you're curious, go check YouTube. Is you can set up like a frequency, like oscillator, and you can change the frequency. So you can make it like 6 hertz, 7 hertz, 8 hertz, 9 hertz, right? And go, right, just start vibrating, right? And maybe have a weight hung over the other end, right? You can watch this thing shake up and down. And at some frequencies, it will set up a standing wave. Actually, one of the videos I have, it's like every 11 hertz. So it's like 11 hertz sets up a standing wave, then 22 hertz, then 33 hertz, then 44 hertz. It's okay. That depends on a lot of things. What's the linear mass density here? What's the weight of this guy? What's the length of the string? There's a lot of factors that go into that, right? Right. Let's look at a guitar string specifically, right? Or I guess any string that you pluck, and piano string, but same idea, right? Is okay, I'm going to put some ideas together starting from the bottom. Okay. Now, if you pluck this string, let's look at this picture. Right? Remember that the wavelength is actually double the length of the string, right? Okay, so let's start with this bottom box right here. The wavelength is actually double the length of the string for setting up that particular standing wave. Okay, you plug the string, right? Now, remember this super important wave formula right here. The speed of the wave is equal to wavelength times frequency, right? And there is an associated speed, right? So, okay, so you can substitute in 2L here. And F, that frequency, hey, that's the note frequency. Maybe you're trying to like pluck an A note, right? Maybe it's like 440 hertz, for example, 440 hertz, right? That would go right there, right? And now to this top box, this kind of yellowish looking box, right? What is the speed just in general of a pulse on any string? Well, it's the square root of the tension in the string divided by the linear mass density. So the mass of the string divided by the length of the string. So like linear mass density. I see that. So when you're tuning an instrument on a string, again, this could be guitar, this could be piano, this could be a violin, right? When you're tuning that string, you're changing the tension. And the purpose is to try to hit a particular note, right? Right, you guys see that, how it all fits together? Okay. All right. A little bit more on music. So let's go back thousands of years ago. I think it was Pythagoras. I think it was one of the things that he was interested in was relationships among musical notes. Like, why do certain notes harmonize together? Right? If you're a musician, you know this. Some notes you play together, like if you play like a tritone interval, it sounds absolutely awful. But if you play like a perfect fifth or a third, then it's like, ooh, that sounds really good. Like it harmonizes, right? But anything to do with harmonies. So I think the story went Pythagoras was like walking along a road and he heard like somebody like banging on pots, like trying to like put pots together. And some of the pots sounded really good together. He's like, ooh, why do those sound good together? And so he started like measuring the diameters of these things and measuring the frequencies and came up with certain frequencies ratios sounded good together. So if you play the same frequency, that could be in music terms what you call the root note, right? Any note could be the root note. It's established like the home base note, right? Depending on the song you're playing, right? Now there are different musical traditions around the world. There's part of music that just has to do with like how you grew up and what culture you grow up in. but pretty much universally, every single culture in the world recognizes the octave, right? Which is exactly, turns out to be double the frequency. So this might be 440 hertz, and this could be 880 hertz, right? Which are both A notes. They're just A notes that are one octave apart from each other, right? And also universally recognized around the world is what's called the perfect fifth interval. And in terms of the physics, that ends up being a 3:2 ratio in terms of the frequency. Okay. All right, then now is where you start to get to different scales. Now, the main standard that's developed around the world is, does anybody know, like on a piano, how many different unique notes there are? 12. Yeah, 12. There you go. Right. Right. And it's, yeah, 13 if you include the octave that it cycles back up to. Right. So, yeah, so 12. Right. Now, if you go to the Middle East, sometimes they even break that down into quarter tones. They actually have 24 different notes. Okay, yeah, yeah. So you know that too. But I guess like the Western scale, right? Western scale. And then usually what you do is you pick out like 7 of those notes, and then I guess 8 if you want to throw in the octave, and you make different scales, although some scales have different numbers of notes. So it's different numbers of notes, right? But you can get, now this table right here is not an exhaustive list, obviously. I'm just showing like 4 different ones, including the octave, right? But a common one, say you play a major chord. One thing that makes a major chord is a what's called a major third, and that's a 5:4 ratio with the original root note. Okay, all right, now that's the Pythagorean type tuning, but it turns out that there's different ways you can tune instruments and different ways historically that it's been done. Giving you guys a little bit of history here. So if you go back, let's say a couple hundred years ago, or like 300 years ago, music sounded different. Like if you play a song today, it's like, oh, hey, this is something that Bach wrote or Mozart wrote. You're not hearing it according to how they heard it. When they wrote a song in a different key, like if they chose, I want to play D, or I want to play like A flat, there was a reason that they chose those keys. And that's because if you use this type tuning, like this Pythagorean type tuning, or this different type tuning, then every key play in has a little bit different sound because the ratios of the notes are a little bit different from each other. So you choose a key, and there were some cases that, here, if you want to play something happy, play in this key. If you want to play something that sounds melancholic, play in this key. Now, modern day instruments, all that goes out the window, and it doesn't matter. You can play any key, and you can just shift the key, and it sounds kind of the same, just kind of shifted, right? And that's because all modern instruments are tuned according to what's called equal temperament, which is this green box down here, which kind of aligns with this Pythagorean, but not exactly. So now, is there any key that sounds particularly melancholic or particularly happy? No, there's no key that does that. They all kind of sound the same-ish because they're scaled logarithmically, or you could say according to exponents. So here, you guys said there are 12 different notes, right? 12 different notes, right? Suppose you, in a chromatic scale, I should say chromatic scale. So suppose you went up, let's start with the root note. The root note would be like note 0. Guys, what's 0 divided by 12? 0. What's 2 to the power of 0? And it's not 0, it's 1, right? So take the root note, let's say 440 hertz, multiply by 1, you get 440 hertz. Great, you got your root note. It is your root note. Great, right? Now let's go up, let's count 12 chromatic notes up. Right? 12 over 12 is 1. 2 to the power of 1 is 2. 440 hertz times 2 is 880 hertz, which would be exactly the octave, right? Guys, it. Right. Now, again, for all the notes in the middle, like for the major third especially is the one that I think is the most off, right? So if you look at the major third in terms of Pythagorean tuning, it should be a 5:4 ratio in terms of the frequency. If you plug into your calculator, I should say the major third, the n would be 4. It's 4, right? 1, 2, 3, 4. Yeah, it's 4 notes up. If you do 4 over 12 and do 2 to the power of that, you'll get a number that's not exactly 1.25. It's off a little bit, right? Anyway, okay, so different ways to tune. Okay, right, you guys got that? Maybe that's more of a history music lesson than physics, but I mean, there's some physics here too, right? Different physics way to define musical notes. Right. How many of you guys ever stood by a sidewalk? Car goes by. You hear that, right? You hear that pitch shift? Now, if you're in the car along for the ride, you don't hear that pitch shift. But if you're standing by the sidewalk, you hear it, right? So what's going on there? Well, let's have a car motion. Let's say the motor's running so you can hear it. Now, if it was just sitting parked, then everybody hears the same note. Let's say, let's just give it like a note, like 400 hertz or something, right? Beep, beep. Right. So everybody perceives the same thing. You're sitting in the car, you're sitting out by the sidewalk, right? But now if you put that thing in motion, right? Now, guys, you put it in motion, the sound waves that are being propagated out into the air, remember, those are going at about 340 some meters per second. Does the speed of those waves change once they've been released into the atmosphere? No, the speed just stays the same. Does the speed of those waves care about whether the car's in motion? No, the speed of the waves doesn't care about whether the car's in motion. But if you're looking at wave crests, those wave crests might be reaching this observer more frequently if the car is headed towards that person, and less frequently if he's driving away from that person. If I drew the observer back here, right? That's a change in frequency. That's like a change in pitch, right? So the frequency observed is equal to the source frequency as long as everybody's sitting at rest, right? But now if you start to put things in motion, you have to multiply by this factor. I got the speed of sound. You can put it in about 340 centimeters per second here and here for 1 atmosphere at room temperature, blah, 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 right? Plus or minus speed of observer, plus or minus speed of source. You have to consider who's moving how relative to whom. Maybe they're all in a straight line, but they could be running towards each other, away from each other. That will help you navigate this plus or minus, okay? And that's called the Doppler effect, right? You guys got Doppler effect? All right, hey, could this car possibly be out driving the very sound waves that it's sending out? You guys ever heard something called supersonic? Super greater than sonic sound? Hey, supersonic, right? Now, suppose you're an observer down here, approximately where this letter, you guys see where the word Mach is? Word Mach, right? Suppose that there was an observer right here where the word Mach is, and the plane already flew overhead. We already watched it fly overhead. Has this person heard that plane yet? No, because none of these sound waves have reached this guy. And when they do, this person is going to hear a what? Sonic boom. Yeah, sonic boom is exactly what I'm looking for. Guess that? Sonic boom. Okay. And when you hear something's flying at like Mach 2, Mach 3, we're talking about a ratio of sounds. It could be like the speed of this, the jet compared to the speed of sound. Right. Now, you guys know from relative motion that if you're sitting inside that plane, what you would experience as g-forces is not the speed of the plane. It's accelerations. So if the plane speeds up, slows down, or goes around a curve, if that pilot makes a left-hand turn, right, you're going to feel that. But if you're just along for the ride, do you guys ever hear of a famous plane in the 1970s called the Concorde? You guys ever heard of Concorde? Right, there used to be a plane that flew over the Atlantic that was supersonic. It was a passenger jet. Now they don't have it anymore. If you were if you were like a boat or an animal in the ocean, I bet you would hear like sonic booms like going across the Atlantic Ocean. Right? So they don't fly that anymore, but they used to. But if you're a passenger inside a supersonic jet, as long as you're traveling a straight line, you just feel normal, right? Yeah, okay. So you guys got supersonic, right? All right, decibels. Right now, I'm just going to guess, maybe like 60 decibels, talking 60 decibels. Okay. What if I talk twice as loud? Is that 120 decibels? No. If I talk twice as loud as I'm talking now, that's closer to like 63 decibels, right? Again, I'm just making guesses for those numbers. There's not anything exactly correct, right? But that's because the decibels is a wave measuring sound, but it's on a logarithmic scale. So 0 decibels actually isn't zero sound. It's just it's like you plug it through this logarithmic formula, right? So we're not going to navigate this exactly, although you could. It's take some thinking, right? But if a barely audible whisper might be like 40 decibels, regular talking might be 60 decibels, really loud music might be 80 decibels. What is 120 decibels? That's about to like blow your eardrums apart, right? And remember, sound is a pressure wave. So it's like air molecules moving back and forth, okay? Right? And this is all like, you can think exponents or logarithms are really just opposite sides of the same coin, right? All right, so that ends sound. Right, now let's move on to another type of wave, specifically light, electromagnetism, right? Now, electromagnetic spectrum, people have divvied these up into these 7 different categories that are all part of the same phenomenon, and they all follow this formula here. Oh, look, speed equals wavelength times frequency. You guys already saw that formula, except now we're using a special character for speed. We're using c, which represents the speed of light, which is like 3 times 10 to the 8 meters per second. Okay, let's get that. Right, now these 7 different categories, let's go left to right here. Now we're going from a long wavelength, also called low frequency, right? Wavelength and frequency are inverse relationship, right? All these are the same speed. They're all the same speed. Speed of light, they're all the same speed. Okay? So left to right, long wavelength, low frequency, to going to the right, short wavelength, high frequency. Okay, you guys see that? So radio waves, then microwaves, then infrared, then visible, then ultraviolet, then X-rays, then gamma rays. Okay, and see that like rainbow portion right there? That is the portion that your eyes can detect, or that human eyes can detect. So the longest wavelength our eyes can detect is 750 nanometers. That's like red. And if you stretch that to like 800 nanometers, it would become invisible to our eyes. Although some animals out there, maybe like some birds or snakes or butterflies, can see like into the infrared, or the ultraviolet for that matter. Right? Some animals can see into the ultraviolet. our human eyes can only see to like 380 nanometers. That's like the shortest wavelength that we can see. Okay. Right. And again, that right there, that is only a very tiny part of this much larger spectrum. Right. What about all these other waves? Here, give you guys an example. You guys ever tune into the radio? Right, let's say FM. Let's say you tune into like 90 point something FM, right? That number has units, right? It doesn't go to what, like 88 to 108, so somewhere in there, right? On the FM, right? Those numbers have units. Do you guys know what the units are on your FM dial? Megahertz, millions of hertz, millions of hertz. Now, if you run the calculation, 3 times 10 to the 8 meters per second, those radio waves are traveling through us right now. You could turn on a radio. I could turn on this radio right now and pick up radio waves, right? They're traveling through us right now. Let's put in like 90 point something megahertz for the frequency. You can calculate the wavelength, and the radio waves that are traveling through the walls right now are approximately 3 meters long. At least the FM radio waves are, right? They're about 3 meters long. Right now, different parts of this spectrum can travel through different materials. So for example, you guys see that glass window on that door right there? Visible light can travel through that glass window, right? That's why you can see it. But what about these walls? What about the ceiling? Visible light doesn't, but I bet some of these other parts do, including radio waves, right? So different parts of the spectrum can travel through different parts. Oh, you know what does not travel through that glass? Infrared, ultraviolet, right? That's why here, if it's a really sunny day outside, you might spend the day at the beach. Do you have to wear sunscreen? Yes, you do. What if it's cloudy outside? Do you still have to wear sunscreen? Yes, you do. But are you pretty well protected inside your car? Yeah, inside your car, you don't have to like wear sunscreen because that glass is going to block the UV, right? Okay, so there we go. There's a crash course on that. All right, let's look at color theory. There's 2 main kinds of color mixing, additive and subtractive. So if you look at your computer screen, TV screen, phone screen, if you get down microscopic, there's really only 3 lights that light up. Do you guys know what those 3 lights are? Red, green, and blue. It's called the RGB standard, red, green, and blue. That's it. Right? And in fact, your eye only has 3 color detecting cones, red, green, and blue. From that, you can make all the other colors. Wait, how do you make yellow? What if you have a yellow screen? Red and green. That's the red and green bulbs light up. Right? What if your screen is black? None. They're all turned off. What if your screen is white? That's all 3 of them. All 3 of them go at the same time. Guess it. You can make all the colors with just 3 color bulbs, red, green, and blue. That's called additive color mixing because the more colors you turn on, the more bulbs you turn on, the more and more it gets to white light. Right? Isaac Newton discovered this, by the way. That you can take white light and split it into the colors. You can take the colors and combine them, make white light again. Okay? Now, that's not true for paint, photographs, your printer. How many of you guys know your printer probably has 4 cartridges. One of them is black, so you can just print black. But you have 3 color cartridges. Do you guys know what your 3 color cartridges are? Exactly, cyan, magenta, and yellow. Yeah, and from that, you can also make any color on paper, depending on how you mix it. How do you make red? Oh, take magenta, yellow, mix it together. Now, this is subtractive color mixing because the more colors you combine, the more light it subtracts out. What if you have all 3 going at the same time? What if you have magenta and yellow and cyan? What color does it make on your paper? Black. So if you run out of black ink, you can still get black. You just have to use your colors, and it's going to use all your colors. Okay, right? And if you don't print any of those colors at all, then it'll just leave the blank white paper. Okay, you can see that. So additive and subtractive color mixing. Okay. Spectral lines. So every element has a sort of like fingerprint, based on its atomic structure of like a light that it will reflect or emit. Right. Now, one way this is useful is in astronomy. You guys ever heard astronomers have discovered a distant planet and they know it has water on it? Like, how would they know that it has water? Right? We don't have a clear image of it. Right? Well, because there's light that goes through a thin atmosphere, and that thin atmosphere has maybe like hydrogen and oxygen in ratios of 2 to 1, which is strong evidence that there would be water molecules in the atmosphere of that planet. So that planet has water on it. Right. Right. So how do we know that the sun is mostly hydrogen and like trace amounts of other things? Well, because the light from the sun has like spectral lines that correspond to hydrogen and trace amounts of other things. Right. Now, these are just the first 8 elements, but every single element has like spectral lines. Okay. Right. So astronomers can use this to figure out what's going on other planets by seeing what's reflecting off the atmosphere. Doppler effect for light. Now, we looked at Doppler effect for sound, right? And it looked kind of like this, but not exactly, right? Doppler effect for sound, the car going by, that jet going by. Whoa. But if you look up into the night sky, now astronomers realized this about 100 or so years ago. I think it was Hubble, was one of the guys who was working on figuring this out, that almost all galaxies are redshifted compared to us, which means that they're moving away from us. Actually, this ties back to the previous slide with these spectral lines, because these spectral lines shift a little bit if they're like what's called redshifted, because they're moving away from us, right? So the frequency shifts, right? In fact, the further away that galaxies are, the more they're redshifted. So that's evidence that the universe is expanding uniformly. And actually, how the universe expands, there's something called cosmological principle. There's no such thing as the center of the universe. Like I used to think that as a kid, like, oh, well, there must be a center and everything's expanding away from the center. No, that's not the case. Either there is no center or the center is sort of everywhere. Yeah, just everything's sort of expanding uniformly in every direction. Right. So it gets weird, but now there is at least one galaxy that's blue shifted compared to us. Does anybody know what galaxy that is? It's Andromeda. So we are inside a galaxy cluster that includes several galaxies. One of them is Andromeda. Some couple billion years from now, Andromeda and Milky Way are going to collide. Let me pause this. Pause. All right, recording is resumed. Okay. Right, so we know the universe is expanding. I'll come back to this later. I've got more on that story. Right. Okay. All right. So you guys good with this? Right. All right. More on optics. Hey, you guys ever put a straw in a glass of water and it looks all bent? Or maybe you gone swimming and your friends look really short underneath the water as you're looking from above. Right. Now, what's up with that? Well, okay, we're gonna put some ideas together. One is called index of refraction. That's this box down here. You guys see N is C over V. Now C is the pure speed of light through a vacuum, and then through air, it's like almost the same thing anyway, right? But V is the speed of light through a material, whether it be water, glass, or something else, right? That's kind of transparent, right? Now the speed of light, isn't the speed of light always the same? 3 times 10 to the 8 meters per second. That's true through a vacuum and basically true through air. But it actually does slow down significantly through like glass and water, which sets up this whole refraction process I'm going to talk about, right? So, like for water, I know this index of refraction is like 1.33, right? So you could say light slows down by like 33%. Glass, there's different kinds of glass, but a commonly used value, you could say like 1.5 for glass, right? Now that sets up this whole refraction thing. It even allows things like microscopes and to work, right? Magnifying glasses, right? Your eyeglasses, if anybody's wearing eyeglasses, right? Your eyeglasses work in part because this is some of the fundamental physics setup that allows us to work. Right? Now, the speed of light changes, but the frequency of those light waves has to stay the same. So if I drew like a transverse wave, light could be like a transverse wave, right? The frequency of that light leaving the air has to be the same as the frequency of that light entering the water. Has to be the same. Well, if speed is equal to wavelength times frequency, and the speed changes, but the frequency is the same, that means the wavelength has to change. And if you run that, again, I know I'm skipping a bunch of stuff because we only got a few days left in school, but this would normally take a few good minutes to explain. You can show that the light has to bend, and that bend, the technical term for that is called refraction. And you can show that the relationship between the indices of refraction, so got N1 could be like air, we'll just call it 1.0, and maybe water could be like 1.33. And these angles, now notice that here's the dividing line between those two media. And I dashed off a normal line. Now, all these angles are measured with respect to this normal line, because normal is perpendicular, right? Got theta 1, theta 2. Call it angle of incidence and angle of refraction, right? Okay. That relationship is given by what's called Snell's law. And this box right here is called Snell's law. So as you were looking into the water, you see a light ray coming from this direction. And your brain extrapolates backwards and say, well, it must have come from back here. So you see the tip of the pencil here. But really, that light ray refracted at that interchange between these two media and came from down here, right? Okay, so the pencil looks short, or if this was a straw, the straw would look short, or if your friend's standing in the pole, right? Okay, you guys get there? Snell's law. If any of you guys teach physics one day, good thing to do is to break out like some glass prisms, a laser, right? You can actually watch. I think I did demo that for you guys. Yeah, I did demo that for you guys. Let's see it. This phenomenon, total internal reflection. Well, if the media that has a higher index of refraction, say you're on that side, like you're in the water, right? At some point, the refracted angle is going to go to 90 degrees and beyond that. So like this light ray is going to be only internally reflected. Now this fisherman up here, is he gonna be able to see the fish? Barely, maybe. Okay. So there might be like one tiny sliver of light that reaches this guy, but it refracts out. Actually, sorry, should be like right about here. It might refract out right from here, go to his eyes here. But he would perceive that fish as being little skinny fish, and he would extrapolate backwards and say, hey, it looks like this fish is right about here. You know, this fish is like way bigger and way deeper in the water. Okay. Right. All right. Let's look at mirrors. One thing I like to do is break out paper and do ray diagrams with classes. Now, we'll do mirrors and we'll do lenses. You guys just get the poster versions of these. So you guys ever look in a plane mirror and you see an image of yourself, you're right side up, you're on the opposite side, equidistant from the mirror surface. You guys see all that, right? This is a plane mirror. You guys see a plane mirror right here? Now, interestingly, suppose this guy's like 6 feet tall. How much mirror does this guy actually need to see his full self? Do you guys see it? You guys see half of his total height? Doesn't he just need this little bit of mirror? You can see the top of his head here. You can see the bottom of his feet here, right? He only needs like 3 feet of mirror. Hey, what if he backs up further away? Or what if he gets closer? Doesn't he need the same amount of mirror to see his entire self? Right? Now, I should say too, there's a bajillion different light rays bouncing off the sky at all different angles. The law of reflection says that the light ray will, the reflected angle will always match the incident angle relative to a normal line. Right? You only need to follow a couple of light rays to figure out where the image is going to be. Right? So I just drew the necessary ones to figure out where the image is going to be. Right? Okay, so if he backs up further away or closer, it doesn't matter. He needs the same spot on the mirror to see his entire reflection, which is going to be half of his height. Okay. Now what if you looked at the back side of a spoon? And I'll tell you what, you guys can try this. You always see the same thing in the back side of a spoon. You see an an upright version of yourself that's smaller. So you appear to be tiny in the back side of a spoon. You will never see anything different. Doesn't matter if you get close or far away. Okay. Is it? Now, one more thing. All right. So this equation. So can you mathematically predict where the image is going to be? Okay. So I got 1 over distance object plus 1 over distance image. Say the distance object is defined as like you measure some distance, right? Now distance image, and here it's going to show up as a negative number because it's on the opposite side. Anything that's on the opposite side, it's called a virtual image. It's going to show up as a negative number. Okay. And this F is called the focal length. Guess I drew like a focal point here, right? So if I measured that, and the focal length is defined as half of the radius of curvature. So if I treat this as like having like some radius of curvature, maybe the radius of curvature is like 10 feet. The focal distance might be like 5 feet. Okay, that's it. Okay. Anyway, so you could mathematically predict where your image is going to show up. Okay. All right. Now let's go concave. Now that that formula still applies. Now you flip the spoon around. Now you can see. Oh, or you know what? I have here a cosmetic mirror. Right. So it's flat on one side, plane mirror, but it's like that shape right there, concave on the other side. Now here you can get one of 2 different outcomes. If your face is really close to it, you always see yourself blown up really big. Right. And this would be a virtual image, upright virtual image. If you hold the mirror really far away, you're going to see what's called an inverted real image. You're going to appear to be upside down, and it's going to look all kind of wonky, weird. Like, hey, like maybe you might be hovering in front of it. Have you guys seen? How many of you guys have not seen this? You guys have all seen this, right? If you haven't, then on your way out today, walk by this because there's a pig down here on the bottom. I got a couple of concave mirrors. Concave mirror here, concave mirror there, right? And it looks like the pig is like hovering above. Right, because it's kind of that bottom picture just like doubled. Yep. It looks like it's just floating above, and it's a really good illusion too. Okay, guys get that? All right. Now let's go away from mirrors. Oh, thank you. To lenses. So this could be like a magnifying glass. Right. Actually, that top one is a magnifying glass. Right. So you guys see see the observer on the right side. Right. He's looking through that magnifying glass at the object, and he sees a blown up image of the object. Now these rays. There are rules for how to draw these rays. I'm going to kind of gloss over that. But if you follow the rules, you see very clearly the magnifying glass will blow up the image, okay, as it should, right? Okay, and then there's other things you can do with these converging lenses, right? A diverging lens, okay, there's only one outcome, so I only drew one image for that. Okay, so you guys see that? If you're wearing eyeglasses, how does this go? I think it's the converging lens is for farsighted and the diverging lens is for nearsighted. There's some version of that. So if your glasses are really thick around the outside, like you're seeing right there, I think you're nearsighted, which is, I think was, okay, right. Anyway, so different ways of making eyeglasses. Telescopes. So Those two on the left are different versions of refracting telescopes. So if you go back to like Galileo, Kepler days, hundreds of years ago, that's what they used. They used different kinds of lenses, right? Line them up different ways, right? And you can get refracting telescopes. Now, one disadvantage of refracting telescopes is that it spreads the colors out a little bit. It's called chromatic aberration. Have you guys ever seen like a prism and like spreads out the light into like different colors, right? Okay. So basically that happens. You can't get really crisp images. So like Galileo was looking at Jupiter and it looked, a little bit fuzzy. The colors were spread out a little bit. Okay, but they just dealt with it. The one on the right, you guys see a mirror here? A mirror? Isaac Newton invented this because Isaac Newton realized, hey, if I use a reflecting mirror instead of just these refracting lenses, I'm going to go with reflection instead. It gets around that chromatic aberration. In fact, all modern day telescopes, like for example, the Hubble, the James Webb, right, they're all modern adaptations of this Newtonian design on the right. Right. Okay. I've got some pictures here. So these are some images that have been gathered with telescopes. Cosmic microwave background. So universe, Big Bang happened almost 14 billion years ago. During the first 380,000 years, it was way too hot at any point in the universe for light to even form or for atoms to form. So right here, what you're looking at is the first time that light was able to form. But again, this was so long ago that it's not even visible light anymore, but it's still in the spectrum. It's just moved on to like infrared, microwave, and radio waves at this point. So scientists have been able to collect that microwave background radiation and get effectively what the universe looked like at year 380,000, which was like when light was first starting to even form. All the red spots are where like galaxy clusters are going to form, right? Here, Hubble Ultra Deep Field. You guys have seen that? That's the same image up there. This is like the edge of the observable universe. Are the galaxies beyond that? Almost certainly. There's a good case to make that the universe is infinite, which is crazy for a whole lot of reasons, but there's only so far we can see because of how the universe expands and the limiting speed of light. Einstein ring. I'm going to come back to this idea later because this involves gravitational lensing, which involves something called dark matter. But this is a galaxy. The galaxy does not actually look like a ring. The galaxy probably looks like a normal galaxy, but there's something called dark matter, like this big spot of something that we can't see that's causing gravitational lensing, kind of like this magnifying glass. All right, so that's going to be our pause point. I'll tell you guys more about this tomorrow. You guys have a great Thursday.